integrals of vector functions. So the definite integral of a continuous vector function r of t can be defined in much of the same way as for real valued functions, except that the integral is a vector. But then we can express the integral of r, the vector function, in terms of the integrals of its component functions f, g, and h as follows. And using the notation of my earlier video, and basically this is my earlier video on integrals / areas under the curve. So basically, and I just want to bring this up because the notation is these are the sample points, is this part right here. So if we had a curve like this, and then basically the whole idea of integrals is you just find the area under it, so you would have geometric shape. So here's just a rectangle like this, but it's using the height of this rectangle is going to be the sample point x1 between a and x1, right there, or x naught there, this x naught or 1. So this is the point there, but the whole idea of this x1 star, it doesn't need to be the endpoint, it doesn't need to be x1, it doesn't need to be x2. So if it was x2, it would go like this. If it was x1, it would go like this. But it's just any point in between them, because there's some different methods. You could do the trapezoid rule or midpoint rule, etc., for trying to get better accuracy and better efficiency on these areas. So so what you'll have is this one is over there. This sample point is anywhere in between. This was on the right side. Notice, and then you would draw the rectangle across it. And that's basically the notation we'll use. All right. So for vector functions, what we'll have is again the same setup. So integral from a to b of this is going to be the r vector of t, like this, and dt. This equals to the limit as n approaches infinity. And now we would just sum these up. So we're going to go summation up to n, and then this is I equals to 1. Yeah, so we're just going to sum up a bunch of rectangles, and be r vector like this, and then the value for the height of it is going to be at the parameter ti star. So it could be anywhere in between t1 and t2. It doesn't need to be t1 or t2. And then delta t like this. And again, from here, this could be as you can view this as delta x, and this height right here is fxi, and in our case, it's going to be r ti star there. Yeah, this xi star there. And again, you just sum all these up, you get the area under the curve. And that would be the integral, as you get an infinite number of these. So in other words, you shrink this delta t to infinitely small, and then you get the integral. And then and since we have components, and typically they're 3-dimensional, what we'll do is I'll just move it over here. Equals to for our setup is limit as n approaches infinity. Yes, n approaches infinity, and this is going to be, now we're going to do all the components, the I, j, k. So we're going to go summation n, this is I equals 1, and now we'll have the f. So yes, this is the x component right here. All right, f of, and then this is going to be ti star, and then delta t, and then this will be like a big bracket there, and then I star is the I component. Now we do the next one, is going to be the same thing. I equals 1. This is going to be g, is the y component. And then put the star better there. Delta t. Oh, whoops. Delta t. And then this is j star. And then keep going. The next one's so I mean F, G, H. So the next one's gonna be H, like that. I equals to 1, and then H of T, I star, like this, and then delta T, and then this is gonna be K. This is the k or the z parameter. I mean the z unit vector. So close this out. Now what I'll do is, and yeah, what I'll do is what I just did was just pause the video and just shrunk it so it fits all in one line. And now, so now that we have these are all just, again, you can put the limit inside every single one of these components. So those are all just going to be the integrals. So for each component, this is the integral of Again, it's going to be the same thing right here. When you sum this up, area is going to be area under the curve as you take the limit approaches to infinity. As the number of rectangles goes to infinity, you basically get the integral. So thus, the integral of a to b of r vector like that, t dt equals 2, and this dt is again just delta t but infinitely small. This equals 2, and then we're going to take, this is going to be integral of just the regular function f, integral from a to b of f of t dt, and then definite integral is just from a to b, that's just what it means. And this is going to be I, and then plus integral from a to b of g of t dt, and then this is j. Now the next one is going to be, again, same thing, integral from a to b of h of t, h of t dt, like that, and this is k, like that. All right, here and I just quickly pause the video, shrunk it again, and we're going to box this whole thing out like this. So this is the integral of vector function. Basically, integral of vector function is just integral of its components. And this means now we can evaluate an integral of a vector function by integrating each component function. We can extend the fundamental theorem of calculus to continuous vector functions as follows. So if it's continuous, there's no breaks in between. So we could extend it out into just this setup like this. Integral from a to b of the vector function r of t dt, this equals to, well, this equals to capital R of t, where this is the antiderivative, in other words, the integral. This is going to be capital R of t as a vector from a to b. And again, what this equals to, just to solve it, integral from integral of b like that. This is a definite integral definition. So recall that from my other videos again, and then subtracted by r of a. So, and this is the antiderivative. And here I just wrote it down. So where capital R is an antiderivative of R, that is R prime. The derivative of capital R is equal to the lowercase r. So basically, the antiderivative. So going backwards. So the derivative of this one is equal to the vector function r. So, and we use the notation, this integral sign r of t dt for indefinite integrals or antiderivatives. That's when we're not evaluating it from a to b. Just in general, just get what the actual antiderivative is. And we'll go over an example on this. So example 5. Integral of a vector function by component. So if we have r of t, the vector function, is equal to 2 cosine t I plus sine of t j, write this a bit better, and then plus 2 tk, then, well, the integral is going to be, so the integral is, so then integral of r, or the antiderivative, r of t dt is equal to, well, the integral of the antiderivative of cosine, that's just sine. So this is going to be sine of t, because derivative of sine of t is just going to be cosine. And now the integral of sine of t, or the antiderivative, that's negative cosine t, because the derivative of cosine is negative sine t, but then so you have to cancel out the negative, so include another negative. So negative cosine t, because again, derivative of cosine t is negative sine t. So we need to cancel that out. J, and then the this one here. So this one here, t, well, 2t, so the derivative of t squared is 2t. So this is going to be t squared, k, like that. But lastly, again, when we deal with this indefinite integrals, we need to include a constant. In this case, it's a vector, so a constant vector of integration, because the derivative of the constant is going to be 0. So basically when we take a derivative, because this whole thing's an antiderivative, so when we take a derivative, we get a 0. So in other words, this is 0 there. So whatever this value of this constant is, it will always be 0. So we need to account for that this could be anything there. And so I wrote that down. So where capital C as a vector is a vector constant of integration, again, because any value that will still fit this antiderivative, or will match this derivative of it. or will become an antiderivative of this right here. So and also, and now we'll just do a quick example on doing a definite integral on that. So the integral from 0 to pi over 2 of r of t dt, well, this just equals to, let's write this better, r like that. This equals to, well, now we just evaluate this whole thing. So we already know the antiderivative, which is 2 sine ti minus cosine tj, and then plus t squared k. And now we're going to evaluate it, and then we can ignore the c because when we subtract them, that just cancels out. So now this is going to be from 0 to pi over 2. So we could plug these inside. So we're going to get a setup like this. We'll have a 2 sine pi over 2 minus 2 sine 0. Like that. Let's put it all for completeness. And then minus, this one's going to be a cosine pi over 2 minus cosine 0. And this is going to be j. And I'll move this over, this whole thing. Move it over here. All right, so we move it over there. And then lastly, this is plus, and then this is going to be a t squared is going to be, well, pi over, pi over 2 squared minus 0. 0 squared is 0, so do that. I'll put another bracket. This is going to be our k. It's good. I just put it for completeness. Now let's just start solving all these. Well, again, recall sine pi over 2. That just goes to 1. So this is 1. And then sine 0 is 0. And this one right here, cosine pi over 2 is 0. It's always, and then cosine 0 is 1. And this one is just pi squared over 4. So this equals to, 2i. And now this next one's going to be minus, this one's a 0, then minus 1, minus negative 1, that's going to be plus 1. So plus j. And then lastly, the last one is going to be right here, pi over 2 squared, that's just equal to, well, plus pi squared, just put that inside, and then pi squared over 4. Okay, yeah, so that is what we get. And we can just box this whole thing in. Yeah, so that is just the definite integral from 0 to pi over 2 of this vector function over here. And here is the indefinite integral, or the antiderivative, and here is the definite one when you're evaluating from 0 to pi over 2.